Hi, Dmytro.
Good afternoon.
Nice seeing you, and thank you for accepting the invitation to be on the podcast on Everyday Metallurgy.
Thank you very much for inviting. It's an honor for me to be here.
Thank you. Yeah, we met this summer at an informal evening dinner, and we fell in discussion about metallurgy. And you told that you have been working on magnesium implants. And I've been looking for a guy who could tell something about metals in the body. So I'm very happy that you accepted my invitation. But first, will you give an introduction to yourself, your name, where you work, and I'm extremely curious to learn a little about the background. How did you become a metallurgist or a material guy?
It's a long story. I don't know exactly what is the best way to start from. If you want from name, maybe you can see it's a Slavic name. So I come from Ukraine, and I come from, well, unfortunately occupied territory by now. But historically, from long time ago, it was the metallurgical heart, if you want, of Ukraine, and largely one of the, if not the most advanced part of metallurgy in the former Soviet Union. So the whole region is a little bit north of Donetsk. There is an area where mostly mining, for coal mining, and Donetsk itself is iron mining, and there is metallurgical plants first built by John Hughes, who was a Welshman long time ago, and he basically created the tradition. Then some major innovations in the business were made actually in this area and then distributed globally. So it is quite a kind of vibrant area from the metallurgy perspective. That largely affected my choice of profession, if you want. But by training, by basic degree, I'm a metallurgist with my master's in metal forming, and my PhD was done on material science and engineering already. And basically all the degrees I got from Donetsk, well, it was an evolution of the time. It was State Technical University, then National Technical University. And then I began working as a research scientist in a research institute for physics and engineering of the National Academy of Sciences, also in the same town. During the PhD, I had some project with General Electric, which I was leading, and then they wanted to continue it. So after I graduated, stayed for a couple of years still working on this project. And then I decided to get some international experience. So I got invited as a postdoc scientist to Osaka University in Japan, spent some time in there, and then a little bit when the professor I was working with moved to Kyoto University. So I spent a little bit of time working there. Then I had enough of Japan. I moved to Australia. Monash University in Melbourne. And that's where I began working with magnesium alloys. So first for structural automotive applications mostly, but then we found some interesting things that can be in it that are more appropriate for biomedical applications. And that's where I got really excited about that. And then focus of research largely shifted to magnesium alloys. Some other materials too, but magnesium is a major part of research now.
But you're not in Australia today.
Yes, true. So after Australia, I felt like Australia is a fantastic country, especially from the private life experience. But professionally, I didn't feel like metallurgist is something much appreciated by Australian society. So I was thinking a lot about that. Basically, my family at the time continued staying in Japan. So I moved back to Japan, to Ritsumeikan University, and I continued my collaboration with Kyoto University, but worked at Ritsumeikan University for another 2.5 years. And then it was enough Asia for me. And I was looking for a place, from the life balance perspective, Japan is a paradise if the only thing in your life is work.
Yeah.
It is true. If you only care about life, it is just professionally, it is absolutely rewarding. It's everything you need for work is there. In Australia, it was kind of flipped over picture. So it is professionally is not that satisfying, but social life is just fantastic.
Yeah.
At least in Melbourne. So I was looking for a better balance. So first I moved to Europe, to Slovenia, where I was working for an interesting, if you want, project at a startup kind of University of Nova Gorica, which at the time was first private university in Slovenia.
Yeah.
So I was working there as a microscopist for some time, for 1 year. And then I was invited to work at Lund University in Sweden as a professor of materials engineering and head of division of materials engineering. So I moved to Sweden in 2015.
Yeah. And that's where you are today.
And I'm here since then, correct.
Yeah. Wonderful. And it was also in Sweden we met.
Exactly.
Yeah. So if we jump into these magnesium alloys, why are magnesium alloys interested as implants in your body?
There are at least two reasons. There are many, but two major reasons that are typically cited in this case. One reason is magnesium is perfectly biocompatible. So it does not, well, the level of toxicity is even difficult to estimate because we have natural content of magnesium in the body pretty high as a background, and we have a lot of magnesium intake in food. So try to measure the level of magnesium which comes to the body from implants. It's not that straightforward.
No.
So there is a lot of magnesium in the body, and when you Google or whatever search you do online for magnesium, first thing you will see is a huge list of magnesia pills or whatever, food additives,
yes,
food supplements. Basically, and I even found on YouTube some channel where a medical doctor, or the guy saying he's a medical doctor, he uses magnesium as a cure for any possible disease. If you have a headache, you have the lack of magnesium. If you have something, it's the lack of magnesium. It was really funny to see. Maybe true. I do not have respective expertise. But so one thing is biocompatibility. Magnesium itself is perfectly biocompatible. So is the products of its degradation. And magnesium oxide is muscle relaxant. It also helps digestion when you have digestion problems. So when you buy some digestion kind of syrup, that whitish color, that's the solution of magnesium oxide in water. In fact, that's how it was discovered long time ago.
Okay.
Another property of magnesium, which is critically important, is elastic modulus of magnesium is very close to cortical bone in the body, in human body, which makes it, in terms of biocompatibility, one of the best materials for structural applications in orthopedics.
Yeah, it's if we compare like stainless steel that has also been used as implant, has a E module of 205 gigapascal.
Correct. While
I think bone is 10, 15?
20 to 40, depending on bone density, porosity. Well, usually between 20 and 40. Yes, you are correct. So still it is 200 nickel-based alloys. Also, titanium implants are used quite widely, but they all have somewhere between 5 to 10 times larger Young's modulus, which leads in some cases to stress shielding. When implants are installed. Basically, it is the separation of an implant from bone under load.
Yeah, so that's why a typical hip implant has a lifetime restriction.
Oh, it is a little bit more complex than
Okay.
that, but this is one of the reasons, yes.
Yeah. Yeah. So then I am curious to learn about it. Are you the main inventor, or is it so new to use magnesium as an implant, or has it been done for many years, or is it done at all today? When came the first idea of using that?
I would say first idea was curious, let's put it this way, curious doctors. Since magnesium got discovered as a metal first extracted by now, 130 years ago approximately. From the moment it was extracted as a metal, and curious doctors testing everything. So they began sticking it to human body.
Okay.
And they tried all sorts of things. So they tried to use it as some structural components. They tried to use it as anti-inflammation kind of drugs, so the needles. And basically, there was no systematic use of magnesium implants in the human body. The applications were random. So one doctor at a time was trying something, was documenting it. And then when he stops experiment, nobody was following it up. So it was over the first, I would say, 100 years, it was very non-systematic attempts, very isolated by different people in different circumstances. So reports were really not consistent. And for many people who are not in metallurgy, magnesium is magnesium. You know, it doesn't matter. It's you need to have certain level of expertise to understand alloys and to even know this word. And those medical doctors apparently didn't have such vocabulary. They were just taking magnesium as a piece of whatever metal they see. It is magnesium. Okay, then it is magnesium. So for a while it was like that. But systematic studies and systematic attempts of using magnesium alloys in biomedical application effectively really started in late 90th of this century. So let's say approximately 3 decades we can count as systematic attempts, and they largely can be associated with the development of wrought magnesium alloys. It's again new arrival in the late 90s of wrought magnesium alloys. Before that, magnesium was mostly used in applications as a cast metal. It has among the best property for casting. Yeah. But then it has problems with processing. And the arrival of new wrought alloys gave rise also to the more opportunities for applications, including biomedical. And that's when it became more and more actively used for biomedical applications. There is still a lot of unanswered questions. And regulatory approval for using in biomedical applications is still very scarce. Effectively, it was one MDR approval, or MDD back then, in Germany. It was a German startup who got it. But since then, things changed quite a lot in European landscape. So from MDD, former regulatory body, now we have MDR. Totally different conditions that are much tougher. And that company, as far as I know, for now still hasn't got MDR approval. But there is another company which is Finnish right now. They got last year, in spring last year, they got FDA, American approval of Food and Drug Administration. And they seem to be on the path now to get MDR approval in Europe now. Okay. That would be the first.
Yeah. And what kind of implants is it? Is it for to help your bone grow, or is it to be there eternally, like a titanium implant? It's there, you get it, and it stays there to your end of life.
Right. If you compare it to other implants that have been around, I would say it is complementary. So what has been before magnesium, well, to answer a previous question you had, is I'm not the first to study magnesium alloys and try to make use of them in biomedical context. But there is quite a number of groups, and in fact, the largest number of researchers doing that is probably in Germany, in Europe. I mean, Switzerland is quite active. There are some attempts in Austria, very strong contender in this space. There are some people in Poland, in Slovenia. Yeah, here and there are some people, but I would say Germany has the largest core group of researchers trying to implement magnesium. As I say, there is a company in Finland. There is a couple groups in Sweden. In Denmark, at DTU, there is one group trying to do something. Okay. In this context, we have conversation at least going.
Yeah.
It is not a mainstream. It is a niche application, as you may guess. When it comes to the specific places where magnesium implants can be used, so these are by far not competitors to titanium. It is rather, as I said, complementary, because if you need a temporary bone fixation, what has been happening before magnesium, and if it is a bone which needs some strength, polymers, biodegradable polymers cannot be used. They're not strong enough.
Okay.
Or permanent metals such as titanium, which is pure titanium, also has an ideal biocompatibility, so it doesn't react. It's perfectly bioinert. Yeah. Magnesium degrades, so it is good because it fully degrades.
And it's bioactive.
Exactly. For example, iron can also be considered biometal because it is not toxic.
Yeah.
But its rate of degradation is very slow. But the main problem with iron is that the end product of degradation is magnesium or iron oxide, which is rust, which is basically particles. And if you have these degraded implant particles in your body, probably it is not the best thing to have. It will be accumulating somewhere under your skin, in the muscle, on the bone, or in some places you probably don't really want to have it.
Yeah.
Magnesium is totally different from that because end product of magnesium degradation is magnesium ions. So magnesium from the implantation place break down to ions. And then as ions, our body has natural mechanisms for removing these ions from the body when it doesn't need it anymore. So then basically in magnesium, you have no residual. Moreover, magnesium, when it degrades in the body, it facilitates the regrowth of bone tissue. So it stimulates the formation of hydroxyapatite. In fact, the majority of natural magnesium in our body sits in the bones.
Okay.
So it stimulates. An ideal application of magnesium is places where temporary implantation is necessary. That means, that means, as you mentioned, hips or some joint replacements, knee replacements, elbow replacements, some plates. Those are titanium. Maxillofacial applications when you need to fix some bones. These are titanium. These are permanent implants. But other cases like finger fractures, for example, or collarbone fractures, or a little bit less loaded if you want, like feet, thumbs, or the fixture of soft tissue to bones. That would be ideal applications for magnesium. Also, what has been tried right now increasingly actively is non-structural applications, like stents, like, bloodstream stents, but also gastric stents.
Okay,
in the body. Different parts of the body where you need to little bit of facilitation or opening of the.
I have a surfer friend who broke his foot, and it got repaired with screws. I don't know if it was titanium or stainless steel screws, But after the bone has grown, he got the cast off, and he had to train. And then after training, he had a new surgery to remove the screws. And because the risk of these screws was that an inflammation could occur, and if that happened, they would cut off his leg.
Yeah.
So for him to use a, let's call it standard stainless steel implant was a risk. So could magnesium be used as a sacrificial screw to support undergrowth like that?
That is spot on. You're just on the perfectly right position. I presume your friend is young enough. So typically what happens in orthopedic surgery is for bone fixation, permanent implants are used. It is stainless steel and titanium mostly these days. And so it depends on many circumstances, but most popular materials are stainless steels like 318 or 316, sometimes 304. So, I mean, it's the same as utensils in your kitchen. That's what they put in your body.
Yeah.
The titanium is a little bit more, and it is titanium which is the same grade as most popular in aviation, in aerospace application. It is T64, 6% aluminum for vanadium, but special modification Li, which makes it reduces toxicity of aluminum and vanadium, basically. So there are four. What happens in such cases is, as you said, for a broken bone, I had the same on my leg when I was 16. So I had a pretty ugly looking on X-rays plate from stainless steel and 4 screws like this. It looked horrible to fix my bone. It was pretty complex bone fracture. So they fixed it. And then, as you say, usually the risk of having, because of the stress shielding effect, having foreign body in the bone is not that good. So because of the risks, especially and also if you have it for too long, then sometimes bones start growing over it. So, and there can be a lot of complications. So if you are under the age of 35, typically, if I remember correctly, you have 2 surgery. One to install the permanent implant, another one to remove it to avoid the stress, unnecessary parts in the body. But if people are older than 35, usually risks associated with the removal are higher than keeping the implant in place. Also considering that the body doesn't grow anymore and there are other. And second surgery is always money, stress, pain, hospitalization. So there is a lot of costs and discomfort associated with any surgery and risks. Right, infection. So ideal case for magnesium are such cases for temporary fixation. And ideal material for that would be the one matching bone regrowth. So when you install it, when the bone is broken, you install magnesium screws, and then as bone regenerates, as bone reconstructs, the implant gets consumed. So it is replacement of one tissue with the other. And by the time the bone reconstructed, the metal disappears. So
and how do you secure the speed of degradation fulfills the speed of bone growth? Do you do that by alloying?
That's the magic of metallurgy. So it is, there is probably difficult to ensure a perfect match, but we do our best. So that is the question which we are trying to answer doing research now. So it depends, the bone regrowth depends on huge number of factors, from physiological to, specific to each patient, to the environment and specific bone condition, age of a patient.
And do you have a one size fits all? Is it one alloy, one heat treatment, one grain size that goes into every patient, or are there different grades depending on age? Oh, you look like a speedy grower, you are a slow grower.
Speedy grower is usually children.
Okay, yeah.
But the field is very moving. So the field right now is relatively young and very dynamic. So titanium, the use of titanium implants, there is a lot of experience. And you might know, especially Sweden has world-based register for hip implants, for instance. So everybody, when somebody tried to introduce new product on hip implants, they all use Swedish register. It is the best documented. It is not the largest database, but it is the best documented database in the world.
Okay.
But such does not exist yet for magnesium alloys. Okay. And therefore, each case is, there is no wide application. As I said, it is only very fresh regulatory approval. The cases are very few to be really build significant or talk seriously about statistics. So we try to normally nowadays, we try to design alloys that degrade as slowly as possible.
Okay.
Because possible complication when magnesium degrades is generation of hydrogen. So if it is magnesium, when it degrades, it splits water.
Yeah.
So it can degrade in aqueous environment, like our bodies are, even without oxygen at all. It just splits water.
Yeah, it takes the oxygen from the water.
Exactly.
Yeah.
Exactly. So in fact, it is maybe two-step or one-step reaction. So we have magnesium converted to magnesium oxide, and then end product is magnesium hydroxide. So it's a little bit more complicated reaction, but whatever happens, hydrogen gets released. And hydrogen, as you know, is very thin gas with very, very small molecules that are very, very permeable in body tissues. So if hydrogen gets released at relatively slow pace, there is no problem. It gets removed just naturally.
Does it evaporate through your skin? Or?
Yeah.
Okay.
It just penetrates through the skin. All the tissues along its way. Exactly. And it is reported that you may have a little bit of swallowing around the implant in the beginning.
Okay.
But it still doesn't impede the reconstruction of tissue. So it works. But if it happens too fast, this can be bad. Then when hydrogen pocket may be created, so if hydrogen gets generated faster, then it gets removed, then a gas pocket may stay. And then if pocket stays for long enough time, so you may have some damage to body tissues and some unpleasant consequences that try to avoid. So therefore, too fast, even if you're a fast-growing bone, fast grower of a bone, you will not get fast-degrading metal.
Okay.
It is okay to have it a little bit slower than the bone reconstruction.
Yeah.
So.
What alloy is it that has been developed for that purpose then?
I can tell you the system, I believe, has the best promise. So usually rare earth elements are something you don't want to have. Although there is the best performing magnesium alloys in terms of property and modern magnesium alloys that are allowed to be used in civil aviation, they normally contain rare earth elements.
Okay, like what?
Neodymium, gadolineum.
Yeah.
This whole spectrum of them that can be useful. They make magnesium stronger. And they often also lead to the reduction of degradation rate. So when it is done properly. The first material which was MDD approved, that had rare earth elements in its composition. But the effect of rare earths on human body is not really well understood. Some people say it is toxic. Avoid it as much as possible. Some people say no, it is good, and there are some reports even that rare earth elements within magnesium alloys attack preferentially cancer cells. So it can be good for patients with cancer. So there are reports, as I said, it's still dynamic field.
Yeah.
The alloys that I believe are most promising are those with calcium, because it is another essential element in the human body, and zinc.
Yeah.
So this in this group, ultra high purity magnesium, some people show that it does not have very high strength. But for most application in the human body, you don't really need records in strength. So it is okay to have relatively low strength.
Yeah.
You can even use, polymers. They're not particularly strong, but still have a lot of places to be used in the body.
Yeah.
So ultra high purity magnesium that shows really low degradation rate, or some materials like calcium, zinc. People try avoiding using aluminium, which is linked to Alzheimer's disease, as you might know, which is a very efficient element for alloying magnesium.
Yes, it is.
In biomedical application, normally you wouldn't find such alloys.
Okay.
So people experimented still a lot. First alloy which was approved is magnesium, zinc, calcium with small quantities of calcium and zinc. Yeah, and then earlier was used with rare earth, but I don't know where they are right now with this material.
Okay. No. And you said previously they were made by rolling, or
casting used to be magnesium alloys used to be designed for casting. One of the most common alloys is AZ91. So that is aluminium, zinc. That is most common, probably example with some modifications to it, cast alloy. And in terms of casting properties, if you compare it to steel and aluminium, for example, at the temperature of casting, cast iron is rather thick. It's like a thick paste.
Yeah.
Aluminium is a little bit thinner. And melting temperature for magnesium and aluminium are very similar. But aluminium is thinner, but it is still relatively thick. It's again, if you want, it's like jelly, or somewhere between paste and jelly.
Okay.
But magnesium at the temperature of casting, if you want, it's like water.
Okay, it's very liquid.
Exactly. And therefore, it is particularly good for cast products. There is a famous example from Ford when they were making wheel for a car. So in steel, they had to cast 5 different components, machine them, and then assemble on bolts. When they decided to replace it with magnesium, they could cast the whole component in one casting.
Okay.
So typically it is high pressure die casting used for such purposes. So what they've got at the end, and why they are particularly happy about it, is instead of having 5 different components, they could get it from one component. And then on top of that, the weight reduced by at least, magnesium by density has just the quarter of that in steel. So they have weight reduction on the vehicle, which means sustainability and fuel economy improvement. And on top of that, they also got cost reduction in production because of simplification of the production process.
Yeah, okay.
So,
but the alloys for implants, are they also casted alloys, or are they manufactured in a different way?
We want to have some deformability. We want to have some technological plasticity and ductility in the implantation. For example, if from our experience, if you work with calcium, magnesium, calcium binary alloys, you already have difficulties cutting screws from that.
Because they break.
Yes, it is brittle.
Yeah.
So you do want to have, that's why zinc is typically added to magnesium to increase ductility, technological plasticity. So you have then casting is not as fast when you add zinc to magnesium, but then ductility improves quite a lot. So then you typical, just to mention 2 typical alloys in industrial practices. Cast alloy is a Z91, as I told you, and very common magnesium alloys for rod composition for sheet metal is Az31. They had 3% zinc and 1% aluminium. So, in biomedical applications, zinc is very common.
Yeah.
It also in solid solution helps controlling the degradation property.
Yeah. Then the big question is always, how do you test this? Do you find do you test on your own kids as the doctors did 100 years ago, or on your own body, or how do you test it? And do you test in vivo?
Well, it all starts, of course, from mechanical property in the lab. That's what we have in my lab, because we are just, first of all, metallurgy lab, right? Working with metallic materials. So first, again, that is a little bit tricky right now with mechanical properties. In the past, for regulatory approval, it was enough to test your material. With modern requirements, you have to test your device, which you are going to implant. So this test becomes less critical. More critical tests become corrosion testing, and you start with standard corrosion testing. So, screening sodium chloride solution in water. Yeah. But the only thing you do compared to traditional corrosion testing is instead of 3.5%, right, common simulation of seawater, you use normally 0.9% sodium chloride, which is physiological solution. The simplest possible, and it helps you to understand the degradation of material itself. So we do corrosion immersion testing normally for that, and then we analyze degradation products on our alloys, and that is first estimate. And then you increase complexity of your electrolytes. Yeah. The most common one, which comes closest, or it is as complex as it can be in terms of composition before you start working with proteins and bacteria, some biological cells, mammal cells. So that is simulated body fluid, which simulates blood plasma. So typically Hank's solution is used for that. And then you start working already with some serums or some more complex solution where cells can grow. But the problem is that when you start, that we don't do in our lab already. So we have some special techniques which we develop with colleagues from other departments. They develop instruments that we need to use. So it's a kind of win-win situation. When they improve their instruments and the information we get from their instruments is richer than can get from standard instruments you can buy off shelf from manufacturers of analytical instruments. There is a lot of research and development work. And then after that, when you've done laboratory scale testing in our metallurgical lab, then if you see the results appropriate, you get ethical approval, and then you can do animal studies. And then animal study, you probably start with rats, or you can do first in vitro experiments with cells. Yeah. And then you can start in vivo studies. So those are positive. You can do in vivo studies with small animals like rats or mice, and then you do rabbits and bigger animals. Okay. And then you collect everything, submit it to regulatory approval. If your results look appropriate for human studies, then you can start with human patients.
And very often when you have a chemical reaction going on, if you remove the product, the reaction product, it can push the reaction thermodynamically towards that. And if you put it in your bone and your bone consumes the magnesium, then is it a driving force to corrode faster?
Well, in human body, fluids are moving. Yes. So what shifts thermodynamic balance in the chemical reaction is, for example, in magnesium in particular, pH factor plays a very important role. So because at pH factor of a human body, which is 7.4, right, neutral. So normally you would have the formation of magnesium oxide. And again, you take care of that in testing, so you account for that. If you have a closed vessel, and you don't remove corrosion product, so that magnesium oxide which forms, it is soluble in water.
Yeah.
So it's dissolves in water and it decomposes into magnesium ions and oxygen ions. So and then you have the increase of alkalinity in your electrolyte.
So the pH will rise.
Exactly, pH rises to 10.5 normally, and when it rises to 10.5 level, then the end product is already not magnesium oxide, but magnesium hydroxide.
Yeah.
So then at 10.5, magnesium ions from the electrolyte bind with water, and water then splits not to hydrogen and oxygen, but to HO group. So, and then magnesium starts precipitating on the surface. Yeah. In the body environment, body's fluids flow. So the pH level is maintained at 7.4.
Yeah.
So, and because body environment is a lot more complex than just sodium chloride, then you have the formation of hydroxyapatite. So magnesium, which degraded, transforms into body tissue or gets removed by body fluids. So at the interface of your implant and the body, you would normally have 7.4 pH level and a lot of other compounds, ionic compounds, that are part of the reaction. And then you have rather dense layer of degradation products forming on the surface implant. And then the propagation of chemical reactions is largely determined by the rate of diffusion through that oxide film or degradation passive film on the surface.
Yeah. Okay. So the driving force is the body liquid that flushes it away.
Fluids, body fluids and the diffusion through of these fluids through the passivation layer you have forming on the implant.
Okay. Yeah.
We have quite interesting studies when we studied in vivo magnesium gadolinium alloy, and we used a range of different techniques. This study was initiated by other people. I was just happy to be a part of it. And with this alloy, what we did neutron tomography, we did X-ray tomography, and we did scan electron microscopy chemical analysis. What we found at the end on implant after in vivo studies in rat model, what we found is that when magnesium implant, it was a screw, gets replaced with the bone, so what we see in the bone, magnesium doesn't exist anymore. It is the part of hydroxyapatite, but gadolinium, which was as a solid solution in magnesium alloy, it remains
in the bone.
In the bone. And more
locally.
Look, if you look like neutron, if you do neutron imaging, which is very sensitive to gadolinium, then you see like a screw intact.
Wow.
So you see, it's really interesting. In neutrons, you see intact screw inside your bone. But if you look with other techniques, like X-rays or electron microscopy, which is not
just bone,
gadolinium is just bone.
Yeah. That's great. Yeah. So that could be a good sign that gadolinium is not really toxic. It's just...
Well, that you don't know. So that's what the conclusion from our study was there is selectivity in the dissolution and the removal of degradation products, and gadolinium certainly stays in the bone. But then other people from the group which initiated this study, they did also toxicology, and they tried this alloy with other environments, and they found that this gadolinium preferentially attacks cancer cells. So it can be interesting to follow up these studies with what actually happens.
Yeah. So, Dmytro, here at the end of our talk, I would like to know, how do you see the future of metallic implants? Will we in the future be cyborgs, half human, half metal, or where will we go?
future is difficult to predict in the first place.
Yeah.
I think there will be a lot of selectivity because, we are developing some technologies that are based on metals that are good. There are places where there is no other options right now. Human body cannot regrow a bone in most places. So therefore, there is no way but to replace it with something else. But besides metallic implants, which we have been discussing so much today, there are other technologies. People are trying to use ceramics, and they try to synthesize hydroxyapatite. Okay. So basically synthetic bones trying to use. There are some groups, including those in Lund University, that are very active trying to develop technology so that to help body regrowing cells. Or they do really interesting studies. We had a project recently on next generation biomaterials, if you want something towards answering your question.
Yeah.
And one of the scientists on this project was a bioscientist, and they tried to grow proteins, which or if you want, kind of pre-building blocks, which they can implant at the place of bone fracture, and that will help the bone to quickly reconstruct. So there are technologies competing to ours. I think as it looks right now, from my metallurgical perspective, there will be probably titanium alloys for application like hips or plates or some screws when permanent implantation is necessary. For joints, I think it will be, when friction pair is important, knees, elbows, and things like that, it was probably cobalt, chrome, molybdenum alloys.
Okay.
So better in these friction pairs.
Not ceramics?
Ceramics, maybe pair of metal with ceramic. There are other issues. Probably we need another podcast to discuss complications from those pairs. And for temporary implantation, I think magnesium is one of the best candidates. But later, I think, of course, we don't want to have anything like that in the body. So end game is to have some tools that would help the body to reconstruct natural tissues.
Yeah. So we can stay forever young.
That's probably extreme. That comes with sociological aspects.
Yeah, wonderful. Thank you very much. I learned a lot today. I was especially amazed with the rare earth alloying elements and put that in your body. I had no idea that was possible.
Yeah. Thank you for inviting me. Really, it was a pleasure talking to you. And your questions make me thinking on different aspects of what we are doing. Among people you work with, you think something, but like people like you who are experts in the field but not on the topic, asking questions, it makes you think twice and thrice on what you are doing and refocus it.
Perfect. Thank you very much.
Thank you, Peter.
Yeah. See you.
Bye.
Bye.
Bye.